Today we're going to be looking at reference angles and the unit circle. Our objectives are to be able to find reference angles, to be able to find the 6 trig function values given a point on the terminal side of theta using a calculator, a unit circle angle measure, and to be able to fill in the entire unit circle with degrees, radians, and their order pairs. So how do you find a reference angle of theta? And again, remember this symbol right here, our Greek symbol, is called theta. So what we're going to do is we're going to graph our angle and then find the acute angle formed by the terminal side of our angle and the x-axis. And the things you have to remember about the reference angle, it's denoted as theta prime, that little line here, we call it theta prime, and it's going to be always an acute angle and always positive. The biggest mistake students make is they give me negative answers and they look at the obtuse angle and not the acute angle. So we're going to go through about 4 examples here to try to find our reference angles. So we've already practiced graphing an actual angle, and we're going to go through and graph this angle right here. We're going to graph angle 237. It's a positive angle, so I know I'm doing a counterclockwise rotation. So I'm going to start my curve. I know here's 180, so I'm going to curve a little bit past halfway and finish my angle. And this is where 237 degrees would lie. But my reference angle is the acute angle formed by the terminal side of my angle and the x-axis. Okay, so most students make a mistake and they go to the y-axis, but it goes to the x-axis. This little angle right here is my reference angle, my theta prime. The curved part, the entire thing, is my theta. Okay, so the big part is my angle where the red little swirl is. This little blue acute angle is my reference angle. So how do I find out how big this is? Well, what I'm going to do is I know this is at 237. I know that if I would have stopped here, that's at 180 degrees. So all I have to do is find the difference between these. So if I go from 180 to 237, that is 57 degrees. That's an acute angle and it happens to be positive. What angle? What quadrant did my angle end up in? Well, 1, 2, 3, so this is quadrant 3. If we look at the second example, it's a negative angle measure. Again, we're in degrees, so I'm going to do a clockwise rotation, and I know this is 180, 270, so I'm going to go a little bit, again, more than halfway, draw my angle. Again, this is theta, but my reference angle is formed by the terminal side, so the side I stop on, and the x-axis. So this angle right here is called my reference angle. So, again, how do I find this? Well, this stopped at negative 320. I know if I kept going, followed my swirl, this would have been negative 360. The difference between a negative 320 and a negative 360, a lot of students write negative 40, but remember this has to be a positive acute angle, so this is a 40-degree angle, and we happen to be in quadrant 1. So what if we're actually in radians now? And again, I always find radians to be easier than degrees, but let's kind of go through and show you how to do this. So again, I'm going to put my initial side on my positive x-axis. This is a positive angle, so I'm going to do a counterclockwise rotation, and remember that in radians this is pi, but since we're dealing with fourths, I'm going to make this 4 pi over 4, which is still equivalent to 1 pi. Now I'm going to start to rotate. This is 4 pi over 4. If I rotate all the way back to the beginning, I'm at 8 pi over 4, which is 2 pi, or 1 full circumference of our circle, or 1 rotation. If I keep rotating all the way over here, that's going to be another 4, so then I'm going to be at 12 pi over 4, but I only need to get to 11. Well, if here's 8 and here's 12, halfway is 10, and then halfway between 10 and 12 is 11. So right in the middle is 11 pi over 4. Again, my reference angle is formed by the terminal side, the side we stop, and the x-axis. And again, to show you, this big swirl is our angle. So how do I find this? Well, if this stopped at 11 pi over 4, and I know if I kept rotating, this would be at 12 pi over 4, the difference is 1 pi over 4, or just pi fourths. Okay, what quadrant do I happen to be in? This is in the second quadrant. Okay. And in our last example, okay, draw my initial side. This is a negative angle, so I'm going to have a clockwise rotation. And again, this is pi, but I'm dealing with sevenths, so this is 7 pi over 7, or negative 7 pi over 7 if my negative rotation, but I only need to go to 1. Well, halfway between 0 pi and negative 7 pi is negative 3.5. So I know I'm definitely in this quadrant over here. I'm not even going to rotate a third of the way, and I can draw my angle. So this is my theta. But I know if I take the terminal side and the x-axis, that's also theta prime. So in this case, my angle and my reference angle happen to be in the same spot. So if I know this is at negative pi over 7, and this angle here, this side, was at 0 pi, the difference between them, again, it has to be positive, is just pi over 7. Okay. And again, it won't always be just the denominator with a 1 in front. It just depends on what you get when you subtract the x-axis from wherever your terminal side is. And this one happens to fall into the fourth quadrant. So how are we going to use this to help us out with solving for sine, cosine, and tangent, or really any of our 6 trig functions? So what if I give you a point, negative 5, 8. So the first thing I'm going to do is graph it. Go with negative 5 and 8. So I'm going to put a point at negative 5, 8. I know that lies on the terminal side of my angle. So I know if I was going to draw an angle, I'd have my initial side, and it would rotate until the side went through this point. And we always assume it's a positive angle unless told otherwise, because honestly, it really doesn't matter if it's a positive or negative angle for what we're doing, but we always rotate in a positive direction unless told otherwise. So I know the terminal side, the side where my angle stops, has to go through that point negative 5, 8. So this is my angle. But I want to find the sine, cosine, and tangent of this angle. Well, this doesn't even make a right triangle. But if you look closely, if I drop down a perpendicular line, I now get a right triangle right here in green. Okay. Now, we just graphed a bunch of angles. Remember this, if I take the terminal side and the x-axis, this is the reference angle. And the nice thing is the sine, cosine, and tangent, or actually any of our 6 trig functions of the reference angle, is equal to the sine, cosine, tangent, or all 6 trig functions of our theta. So I don't have to really see a right triangle with theta, I just have to use my reference angle because they are all equal as far as the 6 trig values go. So now I can fill in my side lengths. I knew this was negative 5, I know this was 8. So what I have is a right triangle. My reference angle is right there, which again gives me the same answers as theta. This is negative 5. This is 8. So the only thing I need to do is find my hypotenuse. Again, we use Pythagorean theorem, so 8 squared is 64, plus negative 5 squared is 25, is going to equal my c, or my hypotenuse squared. If I add this, I get 89 equals c squared. If I take the square root, c equals, now normally we write plus or minus, but for us our hypotenuse is always positive, so I can just keep it as the square root of 89. So now that I have this, I can label my sides, because it's a right triangle, with O for opposite, A for adjacent, and H for hypotenuse, and then solve for my trig functions. So sine of theta, all I'm looking for when I ask for sine of theta is what is the ratio. Well, sine is opposite over hypotenuse, so opposite over hypotenuse. The only thing is we don't like to leave a radical in the denominator. So that means I'm going to multiply top and bottom by root 89, which gives me an 89 in the denominator. 8 and 89 don't reduce, so this would be my final answer. If I want to find the cosine, that's adjacent over the hypotenuse. And again, I'm going to do the same thing. I'm going to rationalize my denominator because we don't like to leave answers that way, and we learned that first semester. So that's going to give me negative 5 times the square root of 89 over 89. Again, those don't reduce, so this would be my final answer for cosine. And the tangent of theta, which again, remember theta, I can still write theta because that's what it's asking for, but I can use my reference angle, or theta prime, to get them. And tangent is opposite over adjacent. And again, just so you know, that's the same thing as putting the negative out front, which we typically do. So we get a negative 8/5. So what if I ask you to evaluate using your calculator? Okay, so how do we actually find the different trig functions using our calculator? So we're not really dealing with a reference angle here so much because we're letting the calculator do all the work. So what you want to do first Turn on your calculator and you always want to check your mode. So my calculator right now happens to be in degree mode. I'm just going to leave it there for right now because I see the first problem has a degree. The way you could tell what mode your calculator needs to be in is if you see this tiny little circle, it means a degree. If you don't see it, it means it's a radian. So I'm going to do the degree problems first because I see that problem 1 is a degree and problem 3 is a degree. Sine of negative 491 degrees. Well, because sine has its own little button right here, I'm just going to hit sine and then type in negative 491 degrees. It knows it's a degree because of the mode. And I'm going to hit enter, and all I just have to write my answer. And I'm going to put the approximate sign because I'm rounding. Negative, I'm going to put the 0 just so you guys can see it better. I'm going to round to 4 decimal places, 7547. And that's all you need to do. Alright, I'm going to go down and do number 3 so I don't have to keep switching my degrees and sometimes, or my mode. Sometimes it makes it easier. So let's go down to this one. Now if I go back to my calculator, I don't see a button for cotangent. Actually, your calculator doesn't have one. But what it does have is a tangent button. And if you remember, tangent and cotangent are reciprocals. So what I could do first is write down what this actually equals. Since there isn't a cotangent button, but all I have, it's reciprocal. The reciprocal of cotangent is tangent. So instead of finding cotangent of 580, I'm going to find 1 over the tangent of 580. And actually, I think your calculator just puts the parentheses there, so you probably don't need one here. So I'm going to type in 1 divided by, hit tangent 580. Again, it knows its degrees. And that's now going to give me my approximation. 1.191, and I'm going to round that 4 decimal places. That would round to an 8. Some teachers and some students use a shortcut key to do the reciprocal, this -1 button. I highly suggest not using that button. Our next section, we talk about inverse, which are these sine -1, cosine -1, tangent -1 buttons on your calculator. It can get extremely confusing. I always find it's best that when you know something is a reciprocal to do 1 over, because that's what a reciprocal looks like. So do 1 over its reciprocal. Okay, I find you make less mistakes. So now let's go to our radian. So I need to hit mode and change it to radian. Now again, remember the only time we have to worry about changing this mode is if we're hitting these 3 buttons. If we're not touching these 3 buttons on our calculator, it doesn't even matter what mode you're in. It won't affect any of your other problems. So again, I see secant. I don't have a secant button, but I know secant is the reciprocal of cosine. So I'm going to actually do cosine of 4 pi over 7. So I'm going to do 1 divided by the cosine, and I just hit 4. You're going to use the pi symbol. Don't do 3.14 because you want it as exact as possible. Divided by 7, close your parentheses, and it gives us an approximation. So since we're rounding, it's going to be approximately -4.49. And if I notice that 9 is going to round up to a 0, which makes it a 4, so 40. Our last problem tends to be the most confusing because it doesn't really look like a radian. And the reason why it says 12.3 is because there was a pi, but someone actually multiplied it out and rounded it. So we have 12.3. And again, there's no little circle, so I know it's a radian. But luckily for us, we have a cosine button. So I'm just going to hit 12.3, close my parentheses, and it gives me my answer. So it's approximately 0.9647. And that's all you have to do. So if you remember from geometry, we had 2 special right triangles. These are going to be extremely important for everything that we do at the rest of this chapter. And they were 30, 60, 90 and a 45, 45, 90. And these are in degrees. So what that meant is if we had a 30, 60, 90 triangle, and I'm not going to go through and show you why this works because you did it in geometry. It has to do with dropping down the altitude in an equilateral triangle for the 30, 60, 90. But there was a pattern to the sides. And if you remember, across from the 30 is our shortest side, across from the 60 is our medium side, across from 90 is our largest side. And again, it's because the smallest angle goes with the small side, largest angle goes with the largest side. I'm going to use the letter P, just, you can use any letter, I'm just going to use P. I'm going to call my shortest side P. If you remember the pattern, the side across from 60 is always the shortest side, P, times the square root of 3. The side across from 90 is always twice the short side, or 2 times P. And that's going to be really important because that pattern holds true for every 30, 60, 90 triangle. Now, if you remember a 45, 45, 90 triangle, again, because these two angles are the same, that means these two side lengths are exactly the same, our two legs of our right triangle. And again, I'm going to call the shortest side P, which means this side is also P because they're equal. If you remember, the side across from 90 has the value of P times the square root of 2. And again, the great thing about this is every single 45, 45, 90 triangle will follow that pattern. And we're going to use this to help us in what we call the unit circle. So what is a unit circle? A unit circle is just what it sounds like. It's a circle, but the radius is 1, and we call the number 1 a unit. Okay, so if we have a circle here, it's always centered at the origin, so here's my origin, and it goes to the right one, up one, left one, and down one, just like we did when we graphed these in the conic section. So if you notice, this points at 1, 0, 0, 1, negative 1, 0, 0, negative 1. The reason why this is so important is because it has a radius of 1, which means if I draw a line going here, that also has a value of 1. And no matter where I drop down, wherever I draw my radius, I can drop down a line and make a right triangle. So even if I draw a radius up here, I can drop down a line, I get a right triangle. I could draw it, over here, drop a line, get a right triangle. I could do something like this, drop it down, get a right triangle. And once I have a right triangle, I can do a lot with the sides using our trig and using our special right triangles. So now that I know what the pattern is with my special right triangles, what is the values going to look like in a unit circle? So if I go back to the unit circle for 1 second, if you notice the hypotenuse for all of these triangles is 1 because each of them was the radius of my circle. So if I go to a special right triangle, I know the radius, my hypotenuse, is a value of 1. So if I know one side of a special right triangle, I can find all the rest. So if you remember in a 30, 60, 90 triangle, this side was the same thing as 2 times P. Well, if 2 times P is 1, that means P is equal to 1/2. And if the 60 side is P root 3, then I'm going to get 1/2 root 3. But that's kind of messy, so what we do is we write it as one fraction, and that's root 3 over 2. So the three side lengths of a 30, 60, 90 triangle in a unit circle is 1, 1/2, and root 3 over 2. So let's do the same thing for our 45, 45, 90 triangle. The side that I know is the P root 2 side. And this is where it can get a little bit messier. But if I know P root 2 is equal to 1, I can solve for P by dividing both sides by root 2. So I get P is equal to 1 over root 2. The only thing is we don't like to leave answers like that, so I'd multiply top and bottom by root 2. And I get a final answer of root 2 over 2. So if that's what P equals, and I know this side is equal to P, and this side is equal to P, my two legs of a 45, 45, 90 triangle are root 2 over 2 and root 2 over 2. So in any 45, 45, 90 triangle in a unit circle, my side lengths are 1, root 2 over 2, and root 2 over 2. So this is a unit circle. It can seem very overwhelming. You will have to, on a quiz and test, be able to fill out this entire thing in but because it's filled with so many patterns, you really only need to know a few values and the whole rest of it fills itself in. So there are 3 parts you're going to have to fill in. One is the ordered pair for the points that fall on the circumference of our circle. You're going to have to fill in the degree, the rotation at each of those points, and you're also have to fill in the radian measure at each of these points. Now you already have a filled out one of these actually in your packet, but I'm going to go through and show you where that comes from to help you out with what you're going to have to do on a quiz. The easiest thing to fill out first is probably the degrees. We're going to start there, and that's these boxes with the little degree symbol. We should know that right here is 0. That's where we always start, and you only need to put a 0 there. Even though when we come all the way back around it's 360 degrees, but typically whenever we get an answer here, we write 0 as our answer and not 360, so I want you to get used to that by putting a 0 there. So how do we fill in the rest? Well, because our only special right triangles are 30, 60, and 45, 45, those are the only angles we care about inside our unit circle, because those are the only ones where we can tell what the side lengths are just by knowing the radius is 1. So let me just show you. This can fit perfectly in here. Well, since this is a rotation of 30 degrees, this point right here is at 30 degrees. Okay. And I can then fit in a 45-degree triangle. Okay, if I have that 45-degree triangle, that means this rotation is 45. That means this is a 45-degree angle. And then the last special right triangle that fits in is my 30, 60, 90 triangle. And again, this is a rotation of 60 degrees, so this point up here is at 60 degrees. Okay. So since 30s, 45s, and 60s are important, that's the rotation we do all the way around. But I know if I go straight up, that should be 90 degrees. Well, again, this is 30, 45, 60. But if you look here, the easiest way to think about it is the bigger spaces are 30 degrees, the little spaces are 15 degrees. 30 degrees, 30 degrees, 15, 15, 30 degrees, 30 degrees, 15, 15, 30, 30, 15, 15, 30, all the way around until we get to 360. So this is 0, 30. There's a 15-degree difference, 15-degree difference, 30-degree difference. This is a space of 30, so that puts me at 120. A small one is 15, so that's 135. A small one is 15, so that's 150. A large one is 30, 180. And that should be a good check because you should know that this is 180 degrees, half a circle. Another big space is 30, so that's 210. Small one is 15, 225. Another 15 is 240. And 3/4 away around the circle is 270. That's straight down. Again, another group of 30 puts me at 300. Small 315. Small 330. And again, plus 30 would put me at 360. But again, we just write 0. So that's the degrees of a unit circle. And that's just breaking it down into all the pairings of 30s and 45s. The next thing I want to fill in are the radian measures. And again, students get really freaked out by radians, but they are very simple to fill out. There's a pattern for them. It's nice and easy. The ones I like to fill out first are the north, south, east, and west, our axes. Because this right here is 0 pi, because that's our starting point. And if you remember, 180 degrees is the same thing as pi, because that's what we use to convert from degrees to radians. This was our conversion. Well, if half a circle right here is pi, if I do half of that, this would be pi over 2. So I know every 90 degrees is pi over 2, or half a pi. So the first 90 is half a pi. The second 90 is 1 full pi. The third 90 is 3 halves, or 3 pi over 2. And then again, if I went all the way back to the beginning, that'd be 4 halves, or 2 pi. But again, we only need to write 0 pi. So how do I fill in all the rest? Well, I'm going to first look at this 30 degrees. Now, I know I have a conversion. So I know that 180 degrees is equal to pi, and that's what I'm going to use to fill in the whole rest of the circle, is just that fact alone. Okay, so let me just write this off up here. I know 180 degrees is equal to pi. But what do I need to divide 180 degrees by to get to 30? Well, I know 180 divided by 6 is equal to 30. Well, if I divide this side by 6, I have to divide this side by 6. So 30 degrees is equal to pi over 6. And that's where the answer comes from. Just by using our conversion and getting both sides to be equivalent by getting the left side to be what I want. So if this is 30 degrees, I know that's the same thing as pi over 6. Okay. Well, let's think about this triangle that fits in here. Okay. That triangle is the exact same triangle that's right here. Same size, which is also the same triangle that's right here, and the same triangle that's right here. So, if this 30 degrees is pi over 6, okay, that means that this space right here is pi over 6. This space is pi over 6. This space is pi over 6. So I can use that to my advantage. If I know that this right here, 180, is at pi, which is 6 over 6, if I have to go back a pi over 6, that means this must have been at 5 pi over 6, because I went back pi over 6 units. Well, if this is 6 over 6 and I go forward pi over 6, that puts me at 7 pi over 6. And if I circle all the way around, if I want to find this is 2 pi, right? So this is normally 2 pi if we go all the way around, which is the same thing as 12 over 6. Well, if I go back 1, I'm at 11 pi over 6. So that's just by knowing this 1 and moving up pi over 6, back pi over 6, up pi over 6, and back pi over 6. I can get my four pieces. Okay. So now what I can do is do the same exact thing, but I'm going to do it for 45 degrees. So let's look at that one. So if I look at 45 degrees, I know 180 degrees is equal to pi. But what do I need to divide 180 degrees by to get 45? Well, if I divide by 4, I get 45 degrees, which means I have to divide the other side by 4, which tells me that 45 degrees is my pi over 4. So just like my 30 degrees was over pi over 6, everything was over 6, my 45 degrees are going to be all over 4. Okay? So how do I figure out this one? Well, instead of looking at this as 6 over 6, I'm going to look at it as 4 over 4, because those are my common denominators now, 4 over 4. Well, if this rotation is pi over 4, then if I go to the middle, that's pi over 4, but I'm going backwards pi over 4, so 4 pi over 4, if I go back 1, I'm at 3 pi over 4. And if I go forward 1, I'm at 5 pi over 4. And again, if I circle all the way around, if I put this over 4, this is 8 pi over 4 because that's 2 pi. If I go back 1, I'm at 7 pi over 4. Okay? So I just have to add 1 and subtract 1 from our either 0 or 2 pi or from our pi. Okay? So those are my 45s. So let's look what happens now when I try to do the 60s. So if I have 180 degrees is equal to pi, what do I divide it by to get to 60? Well, if I divide by 3, I get 60 degrees, which means I have to divide this side by 3. So 60 degrees is the same thing as pi thirds. So pi over 3. That means all of them are going to be over 3. So again, since I'm dealing with over 3, pi is the same thing as 3 pi over 3. Well, if I go back 1, because remember this rotation to these higher points now, or the further ones, the ones that are further away from my x-axis are pi over 3. This is 3 over 3 and I go back 1, now I'm at 2 pi over 3. And if I go forward 1, I'm at 4 pi over 3. One full circle, if I'm in thirds, is 6 pi over 3 because that's 2 pi. But again, if I went back 1, I'm at 5 pi over 3. We're going to be using these families a lot, and I like to remember them in families. So my 30s, if you notice, are over 6. My 60s are over 3, so that's a good way to remember it. The 45s has a 4 in it, it's over 4. My 30 degrees are pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. The 45s are pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. If you notice, they're all odd numbers. And my 60s are over 3. 1 over 3, 2 over 3, 4 over 3, 5 over 3. And we're going to be spending a lot of time practicing these, and in your packets you have a lot of blank copies of this, so you can try to fill them in over and over again. The last thing we need to fill in deals with our degrees. Okay, so if we want to fill in, our ordered pairs. So if we look at these triangles again, so let me just get rid of this inside stuff for you. If we look at the triangle, I notice I can find the ordered pair for this point by thinking about how much I go over, how much I go up. And that's where these side lengths come into play. I went over root 3 over 2, and I went up my y value 1/2. Okay, so there's my ordered pair. Well, how much did I move at the 45 degree angle? Well, I went over root 2 over 2, and I went up root 2 over 2. Okay, so there's that ordered pair. What did I do at the 60 degree? Well, it's actually the same triangle as my 30, it just rotated. This time I went over 1/2, and I went up root 3 over 2. So those are the easy ones, now that I have my triangle. Okay, so how do I fill in the whole rest? And I'm not going to take the time to fill in everything, but I'm going to show you how it's done, and in a second I'll show you a completed one. Well, the easiest ones to fill in besides those, because it's in the first quadrant, is our axes. Remember, this is a unit circle, so this point right here is right 1, up 0. This one is left and right 0, up 1, -1, 0, 0, -1. I would always fill those in first, because those are the easiest. After that, you want to think about your special right triangles, and our side lengths are always like this. The first one's at √3/2, comma 1/2. Our 45, 45, these will always be the same value because it's a isosceles triangle. So √2, √2/2. And then our 60 is just the flip of the 30, 1/2, and then √3/2. Well, how do you fill in the rest? Well, remember that this triangle right here is the exact same as the triangle here. The only difference is it's in a different quadrant. So I'm still going over the same amount I went here. I'm still going up the same amount. The only difference is that in this quadrant, the x's are negative, the y's are positive. And same thing in the quadrant 3. This is still the same. It's still going over the same amount, down the same amount. So the x and y values are the same. The only difference in this quadrant is the x is negative and the y is negative. And then likewise in the fourth quadrant, I'm still going over the same amount, still going down, so the x and y values are the same. The only thing that difference is the x value is positive, the y value is negative. And in quadrant 1, they're both positive. So the only thing that changes for these ordered pairs is the signs. Every single 30-degree reference angle, remember all these have the same angle of 30 degrees, our reference angles, our theta prime, will be √3/2, comma 1/2, except the signs are going to change. Here the x is negative, the y is positive. Here they're both negative, and in quadrant 4 the x is positive, the y is negative. And then you fill in the whole rest. The nice thing about this and what we're going to use to help us solve is, if you remember when we're using our SOHCAHTOA, sine is the opposite over the hypotenuse. Well, if sine is 1/2 over 1, isn't it just 1/2? And cosine is the adjacent over hypotenuse. Well, √3/2 divided by 1 is just √3/2. So the nice thing about the unit circle is every ordered pair, every x comma y, is the same thing as the cosine of theta comma the sine of theta. So we use the unit circle in these values. They actually solve trig values and ratios a lot easier because the x value is the same thing as the cosine of the angle. The y value is the same thing as the sine of the angle. And the only reason that's true is because the hypotenuse is 1. And that's why we use the unit circle. So let me show you a filled-in unit circle. You can pause this and look at this, or you can look at the filled-in unit circle that should be in your packet, but you will need to be able to practice this and be able to complete filling in this entire thing on any quiz. I hope you feel a little bit better about reference angles in the unit circle. We will spend many days in class practicing this, but you need to be able to find reference angles, be able to find the 6 trig function values given a point on the terminal side of theta using your calculator or given a unit circle angle measure, and to be able to fill out the entire unit circle with degrees, radians, and ordered pairs.